because he didn't get the people who showed it to him. Didn't give him enough. All right, should we continue? So we'll do talk about a couple other bits of this using the ideal gas law and some stoichiometry stuff, and then we will not do this stuff. We'll do this on Thursday. So then we'll, whatever time we have left, we can just use for questions or whatever you want to go over before the exam tomorrow. Or master chemistry or whatever. Okay, so let's put all this stuff together. Have you heard of the ideal gas law before? Is that something you've probably gone through in a previous class? It's just the combination of all of these ideas that we can put all these proportionalities together using the equivalence with a constant that kind of offsets everything. So we're not going to go through all that derivation. You can see it in the book if you want. Important thing being the final gas law, where we've got the product of pressure and volume is always going to be equal to the product of the number of moles and temperature times a constant R, which we call the gas constant. So there's the explanation of that equation. R is the universal gas constant. There are units to it, a lot of units, because it has to offset all these other units in there. So it's 0.8206 liter times atmosphere divided by Kelvin times mole. And then there's another gas constant, and you'll always be given gas constants on exams and things like that. But if we convert this to other commonly used units, 8.314 liter torr, or millimeters of mercury, Kelvin mole. So if your pressure is in torr or millimeters of mercury, you use this 8.314 number instead.
Do you memorize these?
No, you don't need to memorize these, although it might make it quicker to do homework if you know them offhand. But I would give you these numbers if you need them. The other thing you can do is, of course, just convert your units, but it's a little quicker if you can just. So let's review what units we're going to use here. For this particular gas constant, that means that we're going to want our pressure to be in atmospheres, volume to be in liters, moles to be in moles, and temperature to be in Kelvin. We're going to use the other gas constant. Everything's still the same, except the pressure needs to be in torr or millimeters of mercury. And I'm wondering now if that number is actually right. So let me check it. No, that's not actually right. That's 62. I remember now why I didn't put it on there in the first place. Another, a perhaps more commonly used one is this one, which actually the volume times pressure actually ends up becoming energy, so joules. The reason this gas constant is important is not so much for these gas calculations, but because it's used in a lot of energy calculations that we'll get into when we talk about quantum mechanics. So I'm just going to put this in parentheses. So you may see that number if you look up gas constant online or something like that. That's generally the first number that comes up. Keep in mind that those are usually not the units that we're going to be using. The units for that, joule per Kelvin mole, or another way of liter times kilopascals per Kelvin mole. So we are going to have to do some messing with units as we work through some of these problems. But as long as we keep things straight, keep things in line, and always have our units written, it shouldn't be an issue. No. That's kind of the weird part about moving the exam to Wednesday, is now we're doing new stuff that won't be on the exam tomorrow. We'll have a quiz on this stuff on this chapter on Tuesday. Homework will be due on Sunday night. All right. So let's look at some sample problems of how we use this. You can probably do this if you've done it before. Sample of hydrogen gas, we're given a volume, we're given a temperature, we're given a pressure. Calculate the moles present in the gas sample. The important part of this is that you can manipulate things algebraically to get the answer you want. So we write down our ideal gas law, and then we can either manipulate it symbolically first, or we can put the numbers in first and then solve for the numbers that we need. So if we manipulate it symbolically first, we're looking for the number of moles. So that's going to be N equals PV over RT, and we plug in those numbers and solve for it. The other way to do it would be to put these numbers in first, if you prefer. Remembering that our temperature always has to be converted to Kelvin, and then solving for N. So in this particular case, I believe N ends up being 0.57 moles of hydrogen. Another way to do these problems are looking at the changes, kind of like what we did with Boyle's law and Charles' law. Yeah. Yeah, sorry. Good. Okay. So another type of problem, kind of like what we did with these other ones, but you can put this all together by recognizing that R is a constant. So if R is a constant, we can solve for R with the gas law like that. And that means that in the same sample, that fraction always has to be the same. So we can set up an equivalence. This usually isn't done with changes in moles, but it could be. So we often see things like this: P1 V1 over T1 equals P2 V2 over T2. You could put the moles in there as well, meaning that if we change one or more of those things, we can calculate the new one of the other. So in this case, we had a volume change, or the volume stays the same, the temperature changes, and then we want, and the pressure stays the same, it's constant pressure. We're heating it up, and we're asking for the change in volume. So since it's constant pressure, we don't actually need all of these variables, right? Because pressure stays the same, so we don't have to worry about that, because that's going to be the same on both sides. So we can do this just like the Charles law problem we saw before, where we've got our volume, our initial volume, divided by our initial temperature in Kelvin. And then our new volume that we're going to solve for and our new pressure, or our new temperature, 359 K. So you solve that out and you get V2 is 4.9 liters. We're going to think about it, make sure it makes sense. If we have a sample of a gas, 3.8 liters, we heat it up. Is it going to get bigger or smaller? It's going to get bigger. Right? Volume's going to go up. Okay, so a couple other sample problems that you can look at for some practice. I don't think we need to do it right now, but same idea. We just plug that into those equations and try to figure out what we get. What to me is a little more interesting and useful in terms of what we're going to actually use these things for, not that those aren't useful equations, they're certainly really important, but we're going to want to know how we can now use gases in stoichiometry problems. And the practice test had some of these, the second practice test has some of these too, where if we have a sample of gas, we're not going to measure that gas necessarily in grams. We might, but more likely we're going to measure that gas in pressure and volume. Because it can be difficult to weigh a gas. I mean, just think about how you would weigh a gas. You have to get a balloon, weigh the balloon, fill the balloon with gas, weigh that, and then somehow get that gas into your reaction system. It's a lot easier to just think about volume and pressure, especially pressure, which for reasons we'll get into later, to talk about how much gas we have. So we need to think of ways, or we need to find ways that we can figure this out. And one of the most important numbers for that is this idea of molar volume. So know this number. At 0 degrees C in 1 atmosphere, an ideal gas, which means a gas that behaves perfectly according to these laws, and as we'll see in a little bit, most gases don't, but it's a good approximation. But at these conditions, an ideal gas will have a volume of 22.4 liters. That's really important because that applies to any gas. Now, any ideal gas, we know that other gases are going to maybe not work that well in one way or the other. Is this going? Yeah. But if it were ideal, it doesn't matter what the molecular formula is, it doesn't matter what the size is, it doesn't matter what the molar mass is. If the gas is acting like an ideal gas, then it's going to have that molar volume. So it's going to have that much volume at those conditions. Those conditions are called standard temperature and pressure, and you need to know that as well. All right, standard temperature and pressure is 0 degrees C or 273 K in 1 atmosphere. So we'll often say things like, at STP, such and such happens, how much of it is there. You should also know, as we talked about before, that this is 760 millimeters of mercury or torr. All right, so let's look at how we can now do a stoichiometry type problem, like will be good practice for our exam tomorrow anyway, but now using these gas quantities. All right, so we're going to decompose calcium carbonate. I think we're actually going to do this in lab. I might be mixing it up with a different class, but some classes here do this. I'll have to look at the instructions again. So we got to first have a balanced equation, and then we're going to, instead of calculating the mass, we're going to calculate the volume of the gas produced. All right, so what's our balanced equation here? Anybody want to start me off? Yeah, so we're starting with calcium carbonate, CaCO3, and that decomposes to form calcium oxide, quicklime, and carbon dioxide gas. So you heat it up, you put calcium carbonate in a crucible or something like that, you heat it up, and it will decompose, and you can measure the change in mass. So we want to form 152 grams of calcium oxide, and we want to know how much carbon dioxide is produced in liters. Or just as volumes, but okay, we'll say liters. So first, it starts with just a normal stoichiometry problem. We need to find the moles of CO2, and then once we have the moles of CO2, we can figure out how much volume that is. So let's do that. 152 grams of calcium oxide. Molar mass of calcium oxide is 56. Let's say 56.1. grams per mole. So that's 2.7 something moles. Do a better job of that here. .71. So we want to produce 2.71 moles of calcium oxide. Based on the stoichiometry in the equation, how many moles of carbon dioxide do we produce? Yeah, same number, right? Because we've got a 1-to-1 ratio in the equation. We've got a 1-to-1 ratio there. All right, so now all we have to do is use that number for molar volume since we're at STP. When we multiply it by that 22.4, that tells us the volume that we're going to have at standard temperature and pressure. So we're going to make 60.5 liters of carbon dioxide. So that molar volume is really important. So it tells us how much we have at that temperature. Look at this one. We've got some methane gas that we're going to combust with oxygen completely. Now the methane gas has a particular volume, temperature, and pressure. And the oxygen gas has a different volume, temperature, and pressure. They react, and then we want to know how much carbon dioxide is formed at a third temperature and pressure. So how are we going to do all that? What do you think we should do first?
You convert them all STP.
We could convert them all to STP and do it that way. Although we still would have to go to, we have to then change it to whatever it's asking for the product. So that's one way to do it. What else could we do here? Well, we should probably start with an equation, right? Because we've got a reaction here. So what's our reaction equation? We want to start out. What are we starting with here? What's methane? No, methane is CH4. So we've got CH4 reacting with oxygen, producing carbon dioxide and water. And we need to balance that. That's right. Yeah. So here's our balanced equation. And now we need to know moles of everything. Once we've got the moles, we can figure out everything else with, we can figure out the volume of CO2 using the ideal gas law. Right? Because volume is nRT over P. We're going to have N when we solve for the chemical equation. We've got R, and then we're told T and P. Temperature is 15 C, pressure is 2.5 atmospheres. So once we find the moles of carbon dioxide, we can use the ideal gas law to figure out the volume at those conditions. That also means that we're going to have to use, so how are we going to find the moles of methane and the moles of oxygen? Yeah, we're going to use the ideal gas law for those too. Right? We've got volume, temperature, and pressure for oxygen, or for methane. Then we've got volume, temperature, and pressure for oxygen. So use the ideal gas law and come up with a number of moles for each of those. See if you can find it. Anybody got some moles yet? Let me know when you find. Everybody get moles of methane? .189. Does that sound right? Yeah. Okay, what'd you get for our moles of oxygen? All right. So which of those two numbers should we use to calculate the moles of carbon dioxide formed? Yeah, so which one's the limiting reactant? Okay. The methane, how do you know?
There should be only 2 oxygens for every 1 methane, and there's a lot more than 2 oxygens.
Yeah, we need 2 oxygens for every 1 methane, which means we need twice as many moles. Twice 0.189 is way less than 1.75. So methane is going to be our limiting reactant. All right, so if we've got 0.18 moles of that, it's again a 1-to-1 ratio with the CO2. So this tells us that we're going to make 0.189 moles of CO2 also. So then the volume for CO2 and RT over P, we just solve for N, so that's 0.189 moles. We know R and T, temperature 15 degrees C, which is 288 K, I think, right? Yeah. And all that divided by the pressure, which is 1.25 atmospheres. Oh, you're right. Sorry, I was looking at the other number. 2.50 atmospheres. So that's 0.189 times 0.0821 times 288 divided by 2.50. So I get that the volume is 1.79 liters. Look right? All right, so that's a good example of how you can use gases in stoichiometry type problems. All right. Let's look at one more thing, and then we'll stop with gases for now. So another way that we can figure this out, or another thing that we can figure out from this, is we can actually find molar masses of gases just from other gas data. We can derive the molar mass. So think about it this way. N is number of moles, right? So molar mass, let's remind ourselves, molar mass is, I'm going to say MW for molar mass, molecular weight, just because, I don't know, mm's is kind of like millimeters of mercury. So we'll say molecular weight, which is the same as molar mass, is grams per 1 mole, right? But another way we could write that is grams, or mass, per moles. Because, yeah, if you actually do the division, it's grams per 1 mole. But we can also just think of it as the amount of mass in a certain number of moles, which always stays constant. The reason I do this is because this number of moles is actually what we call N from our gas law. So if we solve this equation for N, the number of moles, we can also think of that as being the mass divided by the molecular weight. So the number of moles we have of a gas is the mass divided by the molecular weight. So we can rewrite our ideal gas law like this. So our ideal gas law is PV equals nRT. If we sub in this N instead, we get PV equals G, right, or mass RT over the molecular weight. Good so far? See where that's coming from? There will be a point to this. We can also then put volume and molecular weight on opposite sides of the equation. The reason for that is that we can actually end up with density. So let me show you how that works. If we rearrange this equation, we can get pressure times the molecular weight equals the mass times R times T divided by the volume. So if you divide both sides by volume and multiply both sides by molecular weight, that's what you come up with algebraically. And the reason for that is that if you have mass over volume, you have another quantity that we know, which is density. We can write the ideal gas law in terms of molecular weight and density. And we can say that the pressure times the molecular weight equals the density times R times T. And then we can rearrange this and put pressure on the other side to find that the molar mass is the density times R times T divided by the pressure. So that was a lot of just moving stuff around and recognizing some equivalencies. But the advantage of all that is that now, if we're given the density of a gas at known pressure and temperature, we can calculate its molar mass. So if we know density, which we can measure pretty easily, right? You measure the mass, you measure the volume. We did that in lab already. Then we can also calculate the molar mass of that gas. So we can figure out what an unknown gas is just by measuring its mass and volume. All right? or we can calculate the density. So this one asks us to calculate the density. We could do that. I think a more interesting problem. Why did I sign out of my book? All right, well, we're not gonna get that one, but you'll see some practice problems in the test that tell you, that'll say something like, say a gas has a particular mass, a particular volume, particular pressure. What is the identity of the gas? So you can solve for molecular weight to get that identity of the gas. Does that sort of get the idea? Maybe, okay. So we're gonna look at next, I'll probably just wait do this next time. This isn't a whole lot. So we'll do this on, we'll continue on Thursday. We don't have a huge crowd here anyway. Talking about partial pressures and then collecting gases over water. So with the additional 40 minutes or so that we have, is there anything that you want to, as you're here, anything you want to talk about, review, go over?
Go over oxidation states.
Oxidation states, sure. Let's see, should we? You want to like do some problems from that, or do some problems? Okay. Let's see. So one way that I would ask about it, let's look at a reaction. Let me find one here so I can not just make something up. Okay. So let's say that silver metal reacts with hydrogen sulfide gas to produce silver sulfide gas and hydrogen gas. All right. The question is, assign all oxidation states, determine what is reduced or oxidized. Something like that. All right, let's assign oxidation states. What's the oxidation state of silver on the left? 0, right, because it's all by itself there. So that's silver 0. What about an H2S? What gets the priority here? Hydrogen. So what should hydrogen be assigned as? +1. So if each hydrogen is +1, what does the sulfur have to be to balance it out? -2. Okay. Let's go to the other side then. What is the what gets the priority in Ag2S? Sulfur. Yeah. What's sulfur going to be? -2, because it's in that row with oxygen, and there's nothing. There isn't any oxygen in the molecule. So then, what's the silver have to be? +1 each, right?
Quick question.
Yeah.
So even though silver can only be +1, sulfur still gets the priority for oxidation state?
Technically, according to the rules, yes, but right, silver is only going to be +1, so there's not really a question there. You could go either way on that. And then what's the hydrogen oxidation state in H2? 0, because there's just hydrogen there. So we've assigned all the oxidation states. What is reduced? What goes from what is gained electrons?
Silver.
Nope. Silver has lost electrons. So silver is oxidized because it goes from silver 0 to silver +1. That's oxidation, loss of electrons. So what's reduced? Hydrogen, because hydrogen goes from H+ to H0. So going from +1 to 0 is a gaining of 1 electron.
Why is it sometimes that like it wants its subscript, like it'll like ask like what is oxidants, and it makes you put H2 instead of just H.
Yeah, it's because the whole species is really a molecule together. So it's not like the electron is going right into just the atom. The molecule reacts as a molecule. So it can be more correct to say that the H2S is reduced and that the silver 0 is oxidized. Another way that we sometimes write this is we might say that silver, or really without the 0, silver is the reducing agent and H2S is the oxidizing agent. That's really more correct, because the thing is really a molecule together. So even though, yes, it's only the hydrogen atom that's being reduced or oxidized, in this case, it is the compound as a whole that is acting as that. Yeah?
Would they need to like balance it out into like a charge?
Not in this class. Yeah. So we'll, when you have a reaction like this, if you want to balance this reaction, you actually can't just balance it the way that, well, this one I think you can. But often you can't just balance the equation the way that we've been doing it by balancing the masses, because you have to balance the electrons also. So you have to do this thing where you break it down into these half reactions where the electrons are shown, and then you balance those first, and then you go back and you add them together to make the whole reaction. That's next semester's class.
So like, is it like if you're looking for the oxidation state of sulfur, sulfate with magnesium, like magnesium sulfate?
Oh, okay. So sorry. So you're talking about just like with ions. Yeah. Let's look at that. We'll look at that example. So magnesium sulfate is MgSO4, right? We have to recognize that that's an ionic compound that's made up of magnesium 2+ ions and SO4 2- ions, right? Now that we have that, we can also assign the oxidation states. So we can recognize, let's actually use a different example. Let's do it this way. Let's look at ammonium nitrate. Ammonium nitrate, because it's a little bit trickier of an example. Ammonium nitrate is NH4NO3. If I said assign the oxidation states in ammonium nitrate, you can't just look at that molecule and assign the oxidation states, because the nitrogens might actually be different because they're in different ions. So we have to break it up first into the ions and then to assign the oxidation states. So we've got NH4 plus and we've got NO3 minus. And now we can assign the oxidation states for each of those. So nitrogen in this case ends up being, because hydrogen is +1, so you got +1, +1, +1, +1, which means nitrogen has to be -3 in ammonium. But then in nitrate, oxygen gets the priority, so you've got -2, -2, -2, and the nitrogen has to be +5 to balance that out. So whenever you assign the oxidation states of ions, you want to first break them apart into their actual constituent ions before you assign the oxidation states. So ammonium nitrate is in fertilizer, and it's actually the explosive part. You can make explosives from it, because what can happen is the ammonium nitrogen can give electrons to the nitrate nitrogen and form nitrogen gas, which is zero, so kind of in the middle. So it can, and that's a very exothermic reaction because nitrogen is so stable. And so that's why that compound ends up being explosive. The nitrogen gas is released. Yeah.
I think you guys answered this before. Are we going to do like methane and methane naming, like those organic naming?
No, we're not gonna do that. Yeah. We'll do a whole chapter on organic stuff next semester. We might get into it a little bit later when we talk about molecular structure later in this semester, but not the technical naming stuff that'll be. Yeah.
What would we give them on the test?
Okay, so on the test you'll get this periodic table including the names of the elements, so you don't need to know all the names of the elements. On the final, it should be noted you won't be. So the final, because it's a national standardized exam, comes with its own periodic table, and you only get the numbers and the masses and the symbols, and you don't get the names. But you'll get these for this exam. Then you'll also get solubility table, the same one that's from the book that we just have been messing with. And you'll get conversion factors between English and metric units or any other kind of unusual units. You will not get metric conversions, so you'll need to know the metric prefixes. And you won't get any names or formulas except ones that don't fit into the rules, like organic ones with carbon and hydrogen. So I think that's it. Yeah.
What is the average for the national final?
The average for the national final, I don't know, but we scale it according to the national statistics. So the exam has statistics associated with it that are based on the percentile, that kind of thing. And so we scale it according to that.
So I really think you should leave that, because I don't think I would really take this as an national standard.
Yeah, the chemistry ones, they're relatively popular. They're pretty good exams for the general chemistry and organic chemistry exams. So we've used them, we've studied them compared to our other types of exams and found that they do about as good of a job of measuring what we're trying to measure. So it works well. Also helps for comparisons, like if you're transferring to other schools or coming from other schools, that's a recognized standard that, okay, it's got to be the same class if that's your same final exam. The hardest questions? I don't know. It depends what's hard to you. Like, what's hard? Some people think some kinds of things are hard. Some people think other kinds of things are hard. I mean, you can certainly expect kind of full limiting reactant type questions, like we had on the quiz today. You can expect filling in equations. You can expect unit conversions, mass percents, empirical formulas. I don't know, all the stuff we've been doing. For a lot of people, the naming will be one of the harder parts, like having to come up with formulas for all the different things, getting the correct names of things, knowing all those polyatomic ions and their charges. It kind of just depends what you think is hard. Yeah, I don't know. Do you want to just look at the exam? We'll just go through it and you can just tell me which ones you think are hard. We can just shut off the video and like just look at it. Everybody will be pissed if they left.
I mean, we are, we're the troopers, you want to stay here.
That's right.
That's crazy.
The class before this one?
Yeah.
I have not taught it, but yeah, we have.
What is the-
What is this class is kind of like a review.
I don't know exactly because I haven't taught it. A lot of it is like there's no if you've done chemistry before, like in high school, there's no need to take that class unless this is just way.
I took chemistry in high school, and then I took it again.
Yeah.
And got up to 2 different
Like
courses.
intro to chem?
Yeah.
Yeah. It's that class is really it's the pace is different. Like we do the same stuff, but we'll go through stoichiometry problems in an hour or something, and that class will spend a couple weeks, going through it over and over again and practicing and looking at all the different types of it. Things like learning the ions, I just put up a chart and said, hey, here's the ions you have to know. In that class, we spend a little more time going through it and practicing it so I can remember it.
He gave us a laminated periodic table and what we could fit on the back of that. Is what we
Yeah,
used for
so that kind of stuff would be appropriate. Right. So this class is, I'd say the overlap is complete. There's nothing that is missing from this class that you have to get in that class. It's more a matter of how quickly you can get it. And if you've never seen some of this stuff before, it's going to be hard without that background. I would say. He's talking about what we call, I think, chemical principles, which is the class before this, Chem 110. If you haven't taken high school chemistry or you just it's been a long time, you need a little bit of refresher, that's a little bit slower paced course that goes through a lot of the same stuff, just at a slower pace and in a little bit more detail, or I guess less detail.
So the final exam for this and the final exam for the next semester, are the two of them combined sort of equivalent to like the AP Chem test or no? Or yes?
Yeah, I think it's supposed to be. I mean, that's the idea of AP, is that it's like the same as the year of chemistry. Yeah, I think it's supposed to be equivalent.
Okay.
I think there are differences between a college class and a high school class, even if the material is the same, just in the way that the material is approached. But you should be doing the same types of problems, yeah.
Still in high school.
Yeah.
What is wrong?
Well, it's not like
I couldn't take AP Chem, so
it's not like people here are that far out of, like, it's not that big of a difference, right?
1 year.
I did that when I was in high school. They didn't have AP Calc, so my senior year, I had to take it to local college. I liked that the hours didn't overlap, like the times didn't overlap quite right. It was during the year, so I got extra time off, and I always had time to go get donuts before. So I used to sit and eat donuts before calculus.
So you gotta take for chemistry major?
Yeah,
Which college?
you have to take 4 semesters, 1, 2, 3 in differential equations. Some people do.
It's the same after for mine.
Yeah, what's yours?
Engineering.
Yeah, and some people do linear algebra too. It can be helpful. Everybody excited for the test tomorrow? Should be fun, right? Good challenge. Get your brain working a little bit. Yeah.
And then finish I don't think I'll be able to finish the homework.
Tonight? Yeah, I'll change it.
Because now I'm didn't expect it.
It's a big one, yeah. Well, chapter 4 is huge. We've been working on it for a while now.
I think it's because of the timing part too.
Yeah, you have to put
There was
everything
one
in.
problem, there was one problem, it was 8 different equations, and you had to do a complete end-to-end equation for each
Oh,
one.
there's a
Don't
second.
spoil
Yeah.
it.
And that wouldn't be bad, except the way that you have to type it.
The way you have to type it is annoying.
Annoying.
These systems,
There's 2 8 questions. It's just.
yeah.
Two of them?
Yeah, I did
Oh.
2 different places every time. I didn't have the patience to do them both at once.
That is the problem with these systems in general, is the interface needs to get smarter, it needs to get better.
It's not as bad
You
once
can't
you know
know
the
the
keyboard shortcuts, but
It doesn't copy and paste of the format.
Right.
You know?
yeah, I didn't know the keyboard shortcuts, so I was like pressing the button each time, and then I got annoyed, so I finally moved on.
I'm working on my own system. It's not exactly my own, I mean, it's using somebody else's, but like an alternative system that is a little bit easier about that kind of stuff. Because they want to make it look fancy and be fully featured and have the subscripts and superscripts and all that stuff. But it really, is it really a problem if somebody types their answer without superscripts and subscripts? Like it's fine, right? Like when you guys send me emails, I don't know if anybody here has, but some people have sent me emails asking about questions and they just like type it out in line in the email. And like you can figure it out, you know what it says. They should do that. It's even worse for organic chemistry if you end up taking that because you have to draw all the structures. We've stopped using the online homeworks completely in that class because it's just too tedious and frustrating.
The structures.
We will. I'll try to limit it a little bit on the online homework
Oh, I remember my.
because you have to draw the things. But the organic structures are big, so it like takes a while to draw them. And in their software systems, it's just not great.
Yeah, 'cause we used master chemistry for my intro to chemistry class too.
Oh yeah, yeah. So you're a little used to it.
And then I used it for physics 1 and 2. So
Okay, so at least it's all the same system. You get used to it.
just say it's kind of annoying. Or not, I shouldn't say annoying. It's just it's fun. It's not a bad system.
Previous chapters, I didn't need to do them.
No, and a lot of it is done well. And I mean, I think overall it's worthwhile, which is why we do it,
Yeah, it works.
because it works and you get mandatory problems. I think the old way of just having 2 or 3 tests in an exam, and that's like all that gets graded for a whole semester, which is still that way in a lot of schools. But I don't think it works great. I think at the cost of annoying some of the better students, you help a lot of other students out. So,
Well, it's a lot better because it grades it for us. It doesn't take time on your hands. You can put
right. So I can get more,
seen on your lectures.
right.
Stuff like that.
Do more other stuff.
Do the research.
I mean, I'm sure he'd have a lot of fun grading this chemistry.
Oh yeah, I'd love just grading
Go to
homework.
read my handwriting, so.
That's another part of it. The lab reports are fine. Already behind on those, so.
Exactly. I still don't understand English because I don't understand how they can stand it.
Grading
Essays
papers.
and there's so many essays, and probably most of